Hello and welcome to the second video on pet coincidences. And we're going to talk about dimensionality reduction and supervised and unsupervised learning. And you will gain some insight into the physical properties of coincidences, and you will get to know like the intro to dimensionality reduction and a bit on supervised and unsupervised learning. And so this platform is called Kaggle, and you can scroll through the script later if you wish. I think this is the easiest for you to follow my train of thoughts. So, as I said, we will mainly look at PCA, principal component analysis, an unsupervised learning method, and linear discriminant analysis, the supervised learning method. And everything I do here is based on another Kaggle tutorial, which is great. It focuses on how numbers are basically can be detected. And yeah, it's based on this one, and feel free to look into it. The link is here, and I will send you the link to this notebook as well, so you can visit them as well. So, regarding physics, you've probably seen my presentation on YouTube, but just a sum up, there was positron emission tomography, and there were coincidences because of an annihilation. There were two gamma particles traveling outside, and if they both hit the detector, that was called a coincidence. And if that happened, this is a true coincidence. So the two gamma particles just fly out of the patient, both are detected. However, it can also happen that two coincidences or two annihilations take place at the same time. Two of the four gamma particles are detected. So we get basically one coincidence, which is wrong. So we assume that if those two particles happened here in a really, really short time window, so it's 2.25 nanoseconds, that these two particles belong to the same annihilation. And this can happen because you have to inject a high activity into the patient. And this is one of the things that we want to distinguish from our true coincidences. And additionally, there's another thing called Compton scattering, where one of the gamma particles is deflected in a way. And we measure it. Still, it lost a bit of energy. That's described by this Klein-Nishina formula. And it looks really, really complicated, but the main thing to know is if you have a small energy loss, you have a small deviation of the path. So this would not be like a crucial energy loss. It could still be measured. So all of those three type of coincidences take place at the same time. And all we know is that those two detectors here triggered, and we don't know whether it was a scattered coincidence, a random coincidence, or a true coincidence. And this is just what we want to do. So, is a coincidence true, random, or scattered? So, what information do we have to distinguish those three types? We've got the energy, mainly, and we have the time of arrival. So we know when each particle hit the detector, and we also know which detector and which layer it was. We have all the information about the detector. We know a bit about the particle, like the energy and the time of arrival. So let's start with our data set. So so in our data set, we will have the energy of the first particle, the time of detection for the first particle, the energy of the second particle, and the time of the second particle. And now in this exercise, we have a data set. But before we come to the data set, this is just everything. If you're not familiar with Python, this is how we have certain libraries that can help us. So for example, NumPy, pretty standard, doing a lot of linear algebra and a lot of arrays and data handling basically. Matplotlib is for visualization. And this is actually our data set. So this is also available for you. So the dataset itself is called coincidence label, and there's a CSV data, so comma separated value. So you can open those with Excel or whatever you wish. And there's the coincidences data file and there's the label data file. Because what we're looking at here at this data set, it's a simulated data set. So we know which coincidence was which, whether it was a true, scatter, or random coincidence. But we're not going to tell the algorithms. So the algorithms have to figure that out. And yeah, in unsupervised learning, we don't tell them at all. And in supervised learning, we tell them to improve them. What was wrong, basically. Okay, so this is all stored in a data frame. If you're interested in this, yeah, feel free to follow this a bit more in detail, let's say. And let's look in our data set. So this is our data set. As I said, it's in data frame. We had due to the CSV file, we had another column here, which was basically the index, so we just dropped that. And those are the columns actually we have. So there's the time of the first particle, there's the energy of the first particle, and you can see the same thing basically here. So time of the first particle, energy of the first particle, the module it hit, the submodule in that detector, and the crystal ID. So these are basically, this is just which detector it was. This is for the second particle, the time and the energy. Again, the detector identification number. And then we have some things which are calculated from this. So, which is basically the distance from the middle of the scanner. And this is basically the angle. Yeah, basically the angular. So S would be like the distance to the middle of the detector, and theta would be this angle in between here. So this is again calculated from those module numbers, basically. And then there's the attenuation, which is the accumulated attenuation along this line of response. So we have those two detectors, then we would sum up the attenuation of all of those voxels in between. So if this value is high, there's a lot of material in between those two detectors, so it is highly unlikely that it arrived. And if there's no material at all, then it's highly unlikely that it originated from here. If you imagine here, those two detectors, the line of response is called between those two detectors, just going through the air, there's no chance that there was an annihilation because there's no activity. So let's look at the file. So timings, energies. So energy should be around 511 kV because that is the energy of a gamma particle, because that is the energy of the electron and the positron. And yeah, the time 2, the energy, the angle. And here the attenuation, here you can see some high attenuation. And this one, if it's really close to 1, then it basically means just travel through the air. So there's no phantom in between. So we would assume this would be a random coincidence. But we'll find out later. And we can also look it up. So we have our, as I said, it's a simulation. So we do not just have our data set, but we also have the labels corresponding to each. So the zeros coincidence here was a scattered coincidence. This one. The second one was a true, and the third one was a random. So number 3, but it's just the second index because Python always starts with 0. So as I said, this would be a random, which I already know because I worked with that data set for quite some while. And yeah, let's investigate further. What are the timings of the particles, the energies, and the attenuation variable? A bit more. So starting with timing, we created an additional variable in the end called time of flight. So the coincidence time 2 minus time 1. And if you do a histogram of that, then you get this image. So this is 10 to the power of minus 9. So it is 1 nanosecond. Is basically on the x-axis. So we see that most of them have below 1 nanosecond time difference. And there is like a few that have till 2.25, as we mentioned, the coincidence window, which is after here it's cut to reduce randomness. So we can see that there are a lot which are really similar and a few that are way outside, let's say. So, and instead of using this second time axis, actually, we're going to use time of flight, this information here, because it's actually more relevant than the time 2, and it will help us later identify which of our variables are actually interesting. So after that, our file looks something like this. In the end, it's 10,000 rows, so it's 10,000 coincidences, and we have 13 columns, so 13 information, basically. So, as said, mostly below 1 nanosecond. Let's look at the energy next, and this would be the energy of the two particles. So you can see energy 1 is in blue here behind, energy 2 is in front, the orange one, and we can see it is again in mega electron volts. So we would in this case look at 0.511 or 0.511, so somewhere around here. We would expect the peak to be, and it is there. It's interesting to see the orange one, so the energy 2 is a bit lower. Yeah, we'll come to that later, why that happens. Okay, next one, attenuation. So as I already said, we look at the line of response, so the line between the two detectors, and just accumulate the attenuation. And if that happens, so this is the attenuation, basically, and we can see that there's a lot of coincidences that have a peak around 1. So there are a lot of coincidences that just have basically no attenuation or just air. So 1 basically means it is air in between the detectors. And all of these lines of responses go through the patient. Okay, so now we get like a feeling for our data set. And let's first look at PCA. And PCA does something quite interesting. In the end, it transforms your data set into another subspace. And the first thing it looks at are the variables which maximize the differences in the data set. So it is good at highlighting those variables which are really distinct. And yeah, this is before we do anything, we usually normalize our data set. So we transform it. This is called the sklearn library in this case. And we basically calculate the eigenvalues and the eigenvectors. So this means we have no covariance anymore. And yeah, I'm not sure how deep I should go into this, but this is basically the basic which you usually do to eliminate any correlation between variables, which you don't usually want. So we want to find the combination of variables which is best in the end, and first we get rid of the covariance. And yeah, I think I'll include a Wikipedia article or some resource on why this is important. But let's just continue. So what we're doing here is we're getting those eigenvalues, and we're going to display them. So the variance is basically the importance of the new dimension. It's not, this is just how it was. You can expand it if you wish and have a deeper look into it, but basically it creates this plot. So there are different features, so combination of variables, which give you a certain variance. And you can see in our, so this is the black one is the individual variance. So the zeros feature of the first feature is giving us something like 9% of the total variance. And the last feature is just something like 6%, but it is in the end still pretty flat. So there's no real dimension which can be easily excluded, which doesn't mean that those dimensions or those variables will help us distinguishing true, scatter, and random events. It just means that it's hard to combine variables and still see everything that's going on. So there's actually a great example. For example, if you have, I linked it here as well. So have a look into that if you're not familiar with PCA at all. And there are different models on different stages of explanation. But let's just say for here, it doesn't matter that much, the PCA, because the first component has a higher, slightly higher, more information than the last one. But it cannot reduce dimensionality here that well. It's interesting to look at this if we do not and would not do this replacement of the time 2 with the time of flight. Because if you do that, you will see that the first component is slightly higher than the last one. So it basically does that as well a bit. Okay, let's just look at the first 5 components, let's say. So the first 5 dimensions, or 5 variables, which we constructed out of variables we had. And within those 5, we have approximately 50% of the variance in the data. And yeah, we're going to encode truth as 0, which is going to be blue. Going to put scatter as 1, which means just green, and random as 2, which is red. And this creates this plot. And on the x-axis here is the first principal component. On the y-axis is the second principal component. So what you can see here are the first 2 principal components in a diagram, which allows us to see some differences between different coincidences. For example, you can see here large red cloud, which are randoms. And you can see here green, blue cloud, which are scattered and true events. You can also see the red ones are frequently as well here, but this region here is exclusively, almost exclusively, for the red ones. So how does it help us? Not that much. Here, the algorithm itself, the PCA, didn't know that this was a random. I just color coded it that way, but this clustering was done without the knowledge that this was a random or that this was a scatter. It just reduced or it just maximized the difference in the data. But if you have a lot of data, which doesn't matter that much, sorry. In this case, for example, the module ID will be different, basically random for each one, but you cannot really reduce it because you don't really know, is this important or is it just doesn't matter at all? But in the end, you cannot, without knowing whether it's important for being a scatter, random, or true, you cannot just discard it, which will be the thing that our next algorithm can do, because in the next algorithm, the linear discriminant analysis, this is the first thing we do with supervised learning. So we're going to tell him what some kind of coincidences are and how they look like, and it can train those. And it's really simple actually to do that. So it's again an sklearn module, and we can train it and transform our data set that way. I won't go that much into detail how it trains this. I won't go into detail on testing, validation, training data sets. Yeah, but it should just give you an insight in how different supervised learning works than unsupervised learning. So here again, we created the same plot, and here you can see the results. So if the algorithm knew what the in the end it's called discriminant, but it's still a component in a way, so it is still a direction, it's still an image space or a higher dimensional space. What you can see here as well, on the right hand side, we got a really, again, a red cloud, which means a lot of randoms are in the first linear discriminant at high values and less at the lower values. And there's a bit more green up here. So high second linear discriminant means rather it's scattered. And in the bottom, you can see the bottom left till here, you can see the true coincidences. And now you're going to ask yourself, what can I learn from that? So what you can do now is display how these components or discriminants are basically created. So you can look at the transformation matrix. And the transformation that is being done is basically that our original data set, consisting of n rows, in this case, I put 10,000 coincidences in, and there were 13 columns by which you could sort them, as you could see here. So there were exactly. So this is transformed into another image space, and by doing so is basically matrix multiplication. So our n 10,000 times 30 matrix, these were all these time 1, time 2 things. And this transformation matrix, we can look into where's the transformation matrix big and which is important for a certain principal component. So let's look at the indices or the column names. So time 1, energy 1, and all that. And then for the first column, so the basically index 0, and this is all that plays into the first linear discriminant. So these are the values for each of those variables for each event. So as you can see here, those values are really all rather small. But you can see there is one value that strikes out. It's almost double, or it is double of everything else. This is the time of flight information. And what you can see here, so it is a positive number. So if there's a big difference in the time of flight, so between time 1 and time 2, then this will give a large impact on the first component, a positive impact. So all of the coincidences you can see in this right half have got a time of flight difference which is rather high. And those are the random coincidences. As we've seen before, there were a lot of coincidences which had just 1 nanosecond at or maximum of 1 nanosecond between them, and there were some which had up to 2.2 nanoseconds between them. And you can see all of those random coincidences are the ones that had basically more than 1 nanosecond between them, because the phantom itself is really small. So 2 particles traveling at light speed, then you can just obtain around 1 nanosecond time difference. So all of those here are randoms, which makes totally sense. So let's look at the second component. And basically, this is then the y-axis. So about why the green is on top, so the scatter is on top, and the trues are on the bottom, so on the negative side of this component. And we're looking here again. This is again the column names, and these are the numbers associated to them. And you can see here the highest value or absolute highest value are minus 0.5 and around minus 1. And those correspond to energy 1, the second entry, and energy 2, the sixth entry. So here the energy of the particles matters most. So if a particle has a high energy, it's gonna be multiplied with a big negative number. So the higher the energy, the lower they are in the second principal component. which you can see here. So the energy of the true coincidences is higher than those of the scattered coincidences, which makes again totally sense, because whenever one of the coins or one of the gamma particles scatters, it loses energy. It is deflected and loses a bit of energy. Not much, but you can see that the green ones are on average above the blue ones in the second component. So this gives us an indication that this separation in this direction is mainly due to the energy. And this is the great advantage of basically those easy classifiers, that you can really see what is going on. And interesting again, and you can gain more insight from that, you can see here the energy 2 value was way more important than the energy 1 value. How did that happen? Well, what you will, in this case here, so the energy 1 is the energy of the particle arriving first, and energy 2 is the energy of the particle arriving second. So if a coincidence is just in the middle, it is basically a race between the two, and it will be really on the nice edge. But if a coincidence is happening here, then it is a way higher probability that it's measured here before here. In fact, almost certain that it is measured here first. And then the secondary particle, which arrives later, and they both travel at the same speed. So it has to have a higher, a longer way to travel to the detector. And a longer way in this case just correlates with more mass in its way. So it is more likely that the second gamma particle is scattered, because there's just way more material in its way. And yeah, in fact, you can see here that this information is almost twice as important as the energy of the first particle, which I think is pretty interesting. Okay, coming to the end. So you've learned about the supervised learning algorithm, LDA, and how to gain some insight from it, to distinguish coincidences based on the variables you have. And you've seen that it performs better than the unsupervised PCA. You've also seen that it does not make that much sense to use PCA, because a lot of the information cannot be condensed onto less dimensions, but the information doesn't really matter to distinguish true scatter and random coincidence. And all the results of the LDA made sense, and we can conclude if the time delay between the two gamma particles is high, that means it's probably random. And if the detected energy of the gamma particles is low, especially that one of the second gamma particle arriving, it is probably a scatter. And with that, I'd like to conclude and point you to the videos of my colleagues, and hopefully you learned something new today and will learn some more. All right, have a great day.